am Konrad Adams. I am the senior developer for Flood Modeler. And this month is actually quite a landmark month for me. It marks my 25th year with the company, so something to celebrate there, I think. A lot of you will know me from the support desk in the past that I've been part of and still continue to be so to this day on Flood Modeler. I have delivered training courses, but my primary role in Flood Modeler is in the development of the computational engines, and that's what I've been doing for pretty much the last 25 years, or almost 25 years of my life. I am a sometime user of the software, not as much as I'd like to be, but have quite a bit of experience in using it on actual projects. And the last time I used Flood Modeler in anger was on was in preparation of and installation of a lot of flood forecast models for the Environment Agency in England. My background is in mathematics, and I make no apologies for that. This subject is going to be, or this topic is very much a mathematics-led, or it gives you an insight into the mathematics behind the software. And I think there's a great deal of symbiosis with mathematics and engineering. I think engineering without mathematics would be reduced to kind of a lot of trial and error and experience, and mathematics without engineering would be, I'll say reduced, it's probably not the right word, but to sort of a more philosophical or art form. So like I said, I make no apologies for making this this reasonably mathematical, but hopefully accessible at the same time for those of you who get a bit twitchy over the maths. Anyway, so I guess start by introducing the subjects. What are parameters or advanced parameters? And historically, I don't know the difference between what makes a parameter advanced or not advanced. It's something historic. But there are some parameters that are well understood by the modelers, more of the physical ones, or maybe not so physical, such as model time step, the model distance step, or the grid size when we're talking about 2D modeling. Manning's N, roughness coefficient, Weir coefficients, they're all fairly well understood. What I'm going to be talking about this afternoon is, I guess, the more specialist, the more niche ones, the less well known, less well understood parameters, and to try and talk about how to what they mean and what the effect is and why you should change them and why possibly you might not want to. They're often okay left as defaults. We do have defaults for the parameters, but there are reasons why you want to change them. And I guess the thing to point out here is that we don't want to fudge a bad model just by changing the parameters. The parameters should be in conjunction, changed in conjunction with schematization of your model. So quite often, reschematization of your model is the answer, but there are occasions where you might want to change parameters as well. So the default values are typically chosen to be whatever we deem the most appropriate value to be, whether that's like an average. If there's a range of values, we might pick the one in the middle or the most common one. The most accurate or representative one would be another reason. So there may be a standard Manning's N, for instance, that or the one in the middle that you choose, but there is a spread of them. Probably Weir coefficient would be a better one to have chosen there. Sometimes it can be a kind of trade-off between accuracy, stability, and efficiency. So we want all those three to apply, and sometimes we might have to sacrifice one of those to a certain extent to improve one of the others. So there's a nice little trade-off or compromise between the two. And sometimes they are chosen to be backwardly compatible. So it might be that in previous versions of the software, we didn't allow you to change a parameter. It was hardwired as a specific value. In future versions or current and future versions, we may allow you to change that parameter. And it makes more sense for the default value to be what it always was historically. So that kind of like fixed value that it was in the past, but then we allow you to change it in the future, but we still default it to the old hardwired value. So as I said, changing parameters can help improve one or all of the below: the model stability, our model accuracy, and our model efficiency. And hopefully I'll give you a little insight today onto what a few of the specific parameters will actually do. So just sort of step back a bit and just give an overview of some of our solvers, because the parameters apply to our 1D river solver, our 2D or 1D urban solver. So we've got our 1D river model, which is our open and closed channel software, and there's a multitude of hydraulic structures in that represent our basically hydraulic features in our water courses, and several of those have their own individual parameters, if you like, such as our weir coefficients. And those things are kind of generally well understood. There are a couple that I'll come to in the future that may be less so. Then we have our 2D ADI solver, which is our general purpose 2D solver. And we've also got our 2D GPU, which is based on the TVD scheme. And that's more of a shock capturing solver, which kind of handles discontinuities a lot better than the ADI scheme, which I'll talk about a bit in the future. And the good thing about that is it's easily parallelizable. It's easier to parallelize than the ADI scheme, and that's why we've chosen that one to go forward with our with putting it on the GPU. And then we have the 1D urban solver, which is primarily used for our subsurface drainage networks. I'm not going to talk about any parameters on the 1D urban, so the parameters I'm focused on today will be the of those top three, so 1D and 1D river and 2D. I have this list here, and this is one page of 3 that some of you may have seen before, and this is a list of the most common advanced parameters in Flood Modeler 1D river, with a list of why you might want to change them. There, like I said, there are 3 pages, and that's only the most common, the common parameters. I could talk all day, I think, about all the parameters that you could change in flood modelers, and just give you a little bit of a flavor of what can be changed. The ones I'm focusing on today are those 6 that are listed there, and I'll go through each of them in turn on the subsequent slides. I'll just jump straight down to the 7th point. There is, when I originally did this presentation, it was about twice as long as it should be, so I have a whole slide deck of more parameters that I'm able to show today. And yeah, if you've got any questions on any of the parameters that aren't shown here today, then I'll try my best to answer them, and I may even have a slide prepared already for them that I can show. So let's see how it goes. So if you've got any questions, yeah, as Marion said, do drop them in the question box in your GoToWebinar console. So I guess one question is where to find them, and I'm showing the 1D river page here because they're a bit more obvious in 2D, and I'll come to that screen in due course. But on the 1D river software, it's less obvious, so I thought I'd expose it here. So on your simulation run forms, we have a selection of tabs. Now, some of those tabs are not visible by default, so when you first install the software, they will be hidden. So if they are hidden, I guess the first thing to do would be to go to this View tab here, open that menu, and there's a sub-menu option called Tabs, and all the names of all those tabs have got a checkbox by them, which you can turn on to make visible or turn off to make invisible. And the tabs that they're really looking at are ones called parameters, one called advanced parameters. Again, don't ask me what the exact difference is between a parameter and an advanced parameter. And there are some extra parameters on the low flow options tab as well. And maybe a couple of others dotted about the place, but those are the main 3 areas where we'll find our parameters, and especially the 1D river ones I'm talking about today. So again, trying to marry up the kind of reality and software to maths. So the first picture is a fairly obvious one. This is basically what the whole world will see. An open channel river with a few hydraulic structures in there. So that one's fairly obvious, but you as flood modelers will condense that into some schematization of your model that is represented by hydraulic structures, boundary conditions, and river cross sections and the like. So your view is something more akin to that. What I see as a mathematician stroke software developer is a whole bunch of equations. So what we have here at the top two there are our 1D Savanon shallow water equations, which are the conservation of mass and conservation of momentum. We have a Weir equation in the middle there, and they're quite horrible to solve, and they're impossible to solve exactly, except in some very unique specialized circumstances. So they've got all these derivative terms in rate of change of this, and we've got q squared and h to the 1.5, horrible sort of powers and derivatives that are not easy to solve. So the last two equations are kind of how we convert those into something that's a bit easier to solve. So we linearize them and discretize them. So at the end, we're left with a lot more with some linear equations to solve, as in the bottom two. So what that boils down to is what the flood modeler computational engine sees is essentially that a bunch of linear equations there, where we've got a matrix on the left-hand side. We have our unknowns in the middle there. So for 1D, it's our head values and our flow values. For 2D, it'll be our depth values and our velocities in two dimensions. And basically every row in that matrix represents a single equation. So it might be the mass equation for one river section, it might be the Weir equation for a Weir, or it could be the momentum or mass equation for or for 2D. But the idea is that this is now easily solvable, and this is where our computational power comes in. If we throw that system of linear equations at a computer package, then it can solve it. You know, most times, I guess. There are occasions when it can't, but basically that's a lot easier for a computer to solve. Like I said, the principle is the same for 1D and 2D. Everything just basically boils down to something that is easy for a software package, a sort of specialist matrix linear algebra package to solve. And I guess one thing to note is most of those coefficients in the matrix are actually zero, because we got maybe 2,000 nodes in our model. The equations only involve the coefficients at 2 or 3 of those nodes, so you might get about 4 of those coefficients out of 2,000 might be non-zero. So how do we solve basically what is a time-stepping equation? And that generally boils down into two types. We have an explicit solution and we have an implicit solution. And there are good things and bad things about both. So explicit tends to be easier to solve. You're basically projecting your value, your solution at the current time step to be a function of everything that happened at the previous time step or time step. So it's basically, you know what the previous solution was, you can calculate the current solution. Bad things about that is that generally you need a smaller time step to solve that, so it takes longer to solve, and it's generally not as stable or as accurate as an implicit solver. So conversely, implicit solver, we can get away with usually a lot higher time step, but there are disadvantages, and one of those is basically you need to make a guess of the current solution and then improve it, and that kind of is an iterative process, and that itself can save time. But on the flip side, it generally tends to be more accurate and more stable. And Flood Modeler uses pretty much a combination of both of those, the best bits of both, if you like. So 1D and 2D ADI use implicit schemes, or at least partially implicit schemes, and our 2D GPU, which I said is based on the TVD, uses basically a predictor corrector scheme, where the first step is explicit, and then the sort of correction step, the iterative step, is implicit. So hopefully the best of both worlds. And like I said, it's getting a bit mathematical, but hopefully that that gives some insight as to what's actually going on under the bonnet, under the hood of the software. And that brings me to the first advanced parameter that I'm going to describe, and that is theta. That applies to 1D river only, and that is I guess, a weighting between implicitness and explicitness. So our default value is 0.7, a value of 1 would be fully implicit, a value of 0, which we don't allow, would be fully explicit. The minimum value we do allow is 0.5. And why would you want to change this? Like I said, it's one of these where the 0.7 is our best compromise. If we increase it to 1.0, which is its maximum, it's fully implicit. Usually that is more robust, but it can introduce some more time to be solved, and it can introduce some kind of numerical diffusion as well. So there are good and bad things. The other thing is for tidal models, it is recommended to have a lower value of theta of 0.55 for a tidal model. So that's, I guess, the takeouts: increase to improve stability, beware of tidal models where you might need to reduce it, and yeah, beware of the time and kind of maybe numerical wobbles that it might also introduce. So that's our first advanced parameter. I'm going back to a kind of the solution process, mainly for implicit schemes. And this applies, although this diagram is specifically to 1D, the principles to all implicit schemes are very similar. So at the start, we need to make a guess. And our guess at our very first time step is to set the solution to the initial conditions. And that is why generating initial conditions, particularly for 1D river, is very important, because that's our very first guess at our solution. Then we perform our next iteration of the solution. So we step forward in time, recalculate our solution. If we've reached the minimum number of iterations, we can possibly go on, but if we haven't, we need to do, you know, a set number of iterations and keep going. Then once we've reached at least our minimum number of iterations, we need to check how good our solution is. So is our solution good enough to proceed? If it's not, we do it again. If it is, then we step forward in time, set the first guess to our current solution, if you like, so that will now be the previous time step, and perform the whole thing over and over again. There is, I guess, if you've gone through the maximum number of iterations and not got a good enough solution, that's when we issue our convergence warning again. So we do that for every time step until we reach the end of the model, and then hopefully, happy days at the end, we've got a solution. So that's quite a neat little diagram of how the solution process actually works. And knowing how the solution process works enables us to understand what some of the parameters are doing. So there's a couple here that are closely linked. The first ones I'm going to talk about are the iteration control parameters. So that's maxiter, miniter for 1D. And these are the maximum number of iterations and a minimum number of iterations. So we choose this to achieve a nice balance between running our model quickly and running our model accurately. If we have our maximum number too small, then it doesn't give enough iterations for it to converge on every time step. So hopefully it will be converging in 2 or 3 iterations every time step, but there may be a couple of time steps where it's a bit twitchy and we need to go up to our maximum number or towards our maximum number. So our default is 11. It used to be 6. We felt that wasn't enough, and most modelers used to change it to 11 anyway, or at least 11. If the maximum number of iterations is too high, then we run the risk of wasting a lot of time and not really improving our solution. My personal view is if it's not converging in 30 iterations, it's probably won't going to be converging at all. So my recommended maximum would be around the 30 mark. I have seen models with 99, and someone will probably say, yes, well, this model didn't converge in 30, but it did in 50, fair enough. But typically, no more than 30. Default value is 11. Some people like 13, 19. Prime number is always good for reasons I'm not going to go into here. But yeah, choose a prime number, sort of between 11 and 30 is the is a recommendation. And then our minimum number of iterations needs to be low enough or sort of high enough so that the solution is accurate. And I'll talk about that a bit more in the ensuing slide as well. But the minimum number of iterations for 1D River used to be 2. We upped it to 3 a few versions ago, and reasons for that will be explained in the next slide. Conversely, solving the 2D equations, 2D shallow water equations, is computationally expensive. So to have a maximum number of iterations, or to do 11 iterations, would just take probably too much time. So we don't have the concept of a maximum number of iterations, and then testing convergence. What we do for the ADI scheme, at least, is we apply a fixed number of iterations. That's quite typically lower. The default for that is 2, which is this NADVIT parameter, but we can increase it maybe to 3 to do one extra iteration in the hope to get a more accurate solution at the trade-off of it taking more time to do. As I said, the 2D where the 2D advanced parameters is a bit more obvious. It's kind of up front on the 2D run form, as I said. So it's on this options tab under the domains super tab, if you like. So these are there. In the TVD or GPU method, because it's kind of like implicit, explicit, predictor, corrector, then there is a fixed number of time steps. It literally does one predictor correct, one predictor step, and then one corrector step, and that should be sufficient. And because it is partially explicit, when we're not going to get a different solution if we do that kind of twice, if you like, if that makes any sense. Excuse me one moment. So closely allied to this, or used in conjunction with this, is the alpha parameter. And what the alpha parameter does, and this is again 1D River, is to basically calculate a solution, and then it takes a weighted average of that currently calculated solution and the previous calculated solution. And that to me is a bit counterintuitive, like you've spent some time calculating a solution, why do you want to change it? And the reason being is that it can make the solution more stable. What several numerical schemes do not like is sudden jumps, sudden changes, sudden spikes, and that can lead to instabilities. So by kind of relaxing that towards a previously calculated solution, we take like a weighted average that smooths the transition between time steps, between iterations, and leads to hopefully more stable models. I did think when I first knew about this, why isn't alpha equal to 1 by default? And I ran several models and quickly found out why a significant number of them didn't run all the way through, whereas with alpha equals 0.7, they were quite happy. So that's why there is that, why it exists, and why the default is not equal to 1, even though the ideal value is 1, and that's basically always using the calculated, if you like, the exact calculated solution. If we think of the other extreme, alpha equals 0, that would weigh everything towards a previously calculated solution. And that's not allowed for the fairly obvious reason that if alpha was equal to 0, you'd always use 100% of the previously calculated value. So basically, if you take that all the way back to the beginning of your simulation, your simulation results would always be your initial conditions. And that is, that's obviously clearly not right. It would be, as well as being not right, it would clearly be mass non-conservative, and that kind of helps us explain the next piece. So if we think of alpha equals 1 to being our like exactly calculated solution, alpha equals 0 being the previous solution, and then you're taking somewhere in between, and hopefully more than half, because it makes sense to me that you take more of the currently calculated solution than the previously calculated solution. But by having alpha equals less than 1, that does introduce some mass balance or mass conservation issues, so it's not exactly mass conservative. However, the more iterations that you do, the more that weighting is kind of drowned out. So you do more iterations, you're taking more and more of the current time step solution, if you like. So as I said, minimum is or should be a half, default is equal to 0.7, but it can lead to, if alpha's too low, that can lead to mass balance issues. And here's a real example of a reservoir model that I looked at some years ago, and for some reasons, and it was kind of locked away in one of the simulation files, the default alpha value was 0.5, and at the time our default minimum iterations was 2. And the bottom line there, the line in pink there, was the simulated output. The value at the top is kind of like the exact output there. So that's with alpha equals 1. It's a reservoir, kind of like a volume balance model. So it's as close as you'll get to an exact solution in Flood Modeler. So if you think the top line there, the kind of reddy brown one, is the exact solution. The one at the bottom is the pink, in pink is the alpha equals 0.5, minimum iterations equals 2 solution. If we simply increase alpha to 0.7 and keep minimum number of iterations at 2, then we jump to the blue line, so which is the one above, or the third one down, if you like. So that is a whole lot closer, an order of magnitude closer to the exact solution, but it's still probably not as accurate as we'd like it to be. Whereas if we increase our minimum number of iterations to 3, then we get the red line, which is the second one down on the screen. Even though that's not exact, it's probably close enough to the what I call the exact solution, and probably within our other model tolerances as well. So increasing minimum number of iterations to 3 and alpha equals 0.7, that's kind of why those values are the default as they are. And I guess the takeout of that from this is that if you do reduce alpha to 0.5 for stability purposes, then please do increase iterations, minimum number of iterations to 4, and do check your mass balance. So it's okay to reduce alpha, but we also need to do something else to to counter that. So moving on quickly, I appreciate we're running a bit low on time now, are the Froude number limits. So in 1D, these phase out a problematic term in the momentum equation, and that would make your solution go completely unstable and fail at the Froude number exactly equal to 1. So we kind of phase that term out between the lower Froude number limits and the upper one, which are by default 0.75 and 0.9. And what that has the effect of doing is removing that problematic term totally when we get to critical flow. The downside of that is it kind of smooths over the physical hydraulic jump in that. So when it's very critical, when the Froude number is a lot greater than 1, that term is negligible, solution is pretty accurate. At low Froude numbers, that term is completely in there. So again, the solution is accurate, and it just loses a bit of accuracy across that hydraulic jump. We have a similar term that reduces a problematic term in the momentum equation, that is limited by this velocity head threshold value. And that has a very, very similar effect, kind of smooths the transition. However, the TVD solution, and hence our GPU solution, is a shock capturing scheme, and that does capture the hydraulic jump a lot better and exactly, if you like. So there's no need for phasing out any of these awkward terms. So finally, I think the last one I'm going to talk about is the conduit slot parameter. And again, we're going back to 1D River here. And the reason why we need them is that when a conduit reaches, I'm just going to talk about the top slot, even though the principle applies to the bottom as well. But if you're increasing your water depth and suddenly you hit the top of a culvert conduit, then you've got a sudden change from free surface width flow to zero to not having free surface width. And that kind of can jolt the numerical solution and lead to instabilities. So what we allow you to do is to put a kind of a slot in the top of your conduit, which is shaped as per the diagrams here, and that has the effect of smoothing that transition from having a sort of a free surface gradually down to 0 in a smooth way, so that you don't get that sudden jolt. And I guess the reason for mentioning this is that I get asked, or I've seen a lot of models here where people actually change the default values of this these distances, these transition distances, if you like. So the DH, which is your distance below the soffit, and your H slot, which is your distance above the soffit, where it's kind of phased out, if you like. And it's probably not made clear enough, but if you do leave both those values as 0, that basically tells Flood Modeler to use the default values, and those default values are calculated as to effect a smooth transition, as well as preserving properties of the culvert, such as the area and the conveyance as well. So my tip would be use them, please, but yeah, unless you've got a very good reason for doing so, don't change them. 0 means use the defaults, and defaults are there for a reason. And I said that was the last one. I forgot about this one. The real final one I'm going to talk about is the wetting drying depth in a 2D solution. And this is the depth at which a water starts flowing from one cell to its neighboring cell. The reason for doing so is that, are we really interested in, or is it really significant, the flow between cells when the water depth is so low? And all that can do is just increase our or lead to some instabilities. So that's why I have this wetting drying depth, and that's a kind of warm up, if you like, warm up value, so that you can allow the cell to get wet. It doesn't lose any water from it until it's exceeded that depth, and that can increase the stability of your solution. So hopefully, sorry, I'm running a bit low on time here, but in summary, the model parameters can be used to improve your solution. Hopefully I've given you a flavour of their meaning and their constraints, and understanding that is important to knowing what effect they have on your outputs. And like I said, I could speak all day on the advanced parameters in Flood Modeler. But it's also very important to consider our model schematization. As I said at the beginning, often it's better to look at schematization of your model rather than definitely better than fudging a bad model with numerical adjustments, if you like. But it does have a place for in improving your model. The defaults, they are there for a reason, so don't change them unless you've got a good reason, but they are just defaults and we do allow you to change them. So understanding what you're doing is important, and by all means, if you understand them, yeah, then do feel free to change them.